What if I told you there is a mathematically rigorous way to assign a specific limit to a sequence that never actually converges? A standard sequence smoothly approaches a limit, but the sequence 0, 1, 0, 1 bounces back and forth endlessly. Ordinary epsilon n convergence fails here. By smoothing out these endless fluctuations, we extract a measurable, generalized limit, stabilizing right in the middle, at 1/2. We do this using a matrix summability method, or a method. It transforms a divergent sequence into a new sequence by taking an infinitely weighted average of its terms. We multiply an infinite matrix A by a column vector x representing our bouncing sequence. Using the Cesaro matrix, populated with fractions, each row calculates a running average. Row by row, the outputs emerge: 0, 1/2, 1/3, funneling smoothly to exactly 0.5. Matrix methods successfully map divergent sequences to generalized limits, but that raises a critical problem. If we apply these averaging matrices, how do we guarantee they won't distort the limits of sequences that already converge? To answer that, we frame the matrix operation using functional analysis. The space of all convergent sequences becomes our normed space, C. The entire matrix A acts as a linear operator on that space, and each individual row multiplication acts as a bounded linear functional. We call a summability method regular if it perfectly preserves original limits. If a sequence already converges to a value L, the matrix must output a sequence that also converges to L. To determine if a matrix is regular without testing infinitely many sequences, we rely on the Toeplitz limit theorem. It provides 3 mechanical conditions that any infinite matrix must satisfy. First, the terms in each column must eventually approach 0. Second, the sum of the elements in each row must approach 1. And third, the sum of the absolute values of the elements in any row must be bounded by a strict constant, gamma. The Toeplitz theorem turns the abstract problem of generalized limits into a concrete, checkable checklist for any matrix. Let's break down how Kreyszig proves this in the text, starting with necessity. If we assume a matrix is regular, we must prove it meets those 3 conditions. We will focus specifically on proving that the absolute row sums are bounded. Look closely at this formula. Kreyszig constructs a highly specific sequence designed to force the functional to output the sum of absolute values. By aligning the sequence terms to match the signs of the matrix row, the multiplication mathematically cancels out any negative entries. As a result, the output yields purely positive terms, the absolute sum of the row. And because the functional itself is bounded by the uniform boundedness theorem, this absolute sum must also be bounded below a strict ceiling. Now for sufficiency. If we know the 3 conditions are met, how do we prove the matrix is regular for every possible sequence in space C? The strategy relies on this volume representing the entire sequence space. We start with a dense subset inside it, consisting of simple sequences that eventually become constant. The proof establishes that the limit holds on this inner framework first. Since our third Toeplitz condition ensures the sequence of row functionals is uniformly bounded, we can bridge the gap from the dense subset to the full space. Because it is dense, any sequence in the space can be approximated with arbitrary precision by elements we've already solved, proving that the weak star convergence holds across the entire space. We leverage weak star convergence on simple, dense subsets to prove global properties for massively complex infinite matrices. This table compares our 2 approaches. Ordinary convergence is a strict point-by-point test that fails on oscillation. Summability uses a matrix-based approach specifically designed to handle and smooth out those fluctuations. For competitive exams like IIT JAM or CSIR NET, it is essential to distinguish the objects in play. Regularity is a property inherent to the matrix operator itself, independent of whichever specific sequence you choose to test. Memorize the Toeplitz limit theorem with this rapid checklist: columns to 0, rows to 1, absolute rows bounded by gamma. Summability smooths out divergence. Functional analysis provides the operator framework, and Toeplitz gives the mechanical test to ensure the math works properly. Keep learning mathematics by checking out our other chapter-wise breakdowns. Hit the like button, subscribe, and ring the notification bell to stay updated. See you in the next video.